Okay, so today we're going to talk about question answering and how AI can solve it. So question answer is one of the core tasks of natural language processing. And the definition is very straightforward. So you have a question, you want to answer back, right? But this challenge here is you want a direct answer. You don't want a list of pages that you still have to read and get the answer for these pages, but instead you want a direct answer. And not only that, you want to answer in natural language, right? That's how humans do. Let's say, for example, you have a coworker and he's working on a financial report. If you ask him any question about that document, he's probably going to give you an exact answer about that, right? So that's the goal. And the motivations for the business for those kind of technology is tremendous. So you can have fast access to your knowledge base. So everything, every system you have in a company, you can extract information really quick. So that's very helpful for decision making. It's very helpful for automate repeated tasks is very helpful for speed up processes. So there's a lot of benefits in this way, and also it can improve the user experience, right? Let's say you can provide the user the ability to make questions about their orders, make questions about products, specifications. So it increases the usability a lot, and in the very end can increase retention, right? So the thing that usually business wants is some kind of tool like this. And there's two methods. Let's say that one's called local QA. Local QA, it looks at the text and try to extract phrase from the text that is more related to the question. So if the text has the answer, usually it's going to give back the answer, right? And if the text do not have the answer, usually, or it does not return the answer, or return something that is not correct, it can return something that is not related with the question, right? But those methods are way simpler, way faster to be created. And the other model is called global QA. So global QA is able to look for your question, and if the text did not have the answer, he can look the general knowledge base and provide you an answer anyway. So this model is also able to be more abstractive, so they can generate text and it can paraphrases whatever you have in the text. So it's more like humans do, right? So we can express ourselves using our own words. That's pretty much the idea of the global QA. There is pretty much three technologies for that. One is called classic QA. So this is based on statistics approaches. So the idea is that you can rank sentences and just give back the sentence that is more relevant to the question. So these use algorithms like TF-IDF, BM25, and others. The drawback of the advantages of this method is that it's usually it's fast, don't need training, right? And the disadvantage is that usually they are not so precise as like modern approach. And then you have neural extractive QA. So this is based on deep learning in neural networks. So those models are able to understand the meaning and the relation of the words. So they are way better to recognize patterns. So they are way more accurate. However, they are way more computational request way more computational power, and sometimes they are slower. And depending of your data, you need to train your own model. So you have way more complex architecture in this way. But a lot of models, they like platforms like Hugging Faces. There is a lot of pre-trained models that probably is going to be able to do most of the tests, right? So we have models like Roberta, Stilbert, and others that are already pre-trained models. The last technology is the generative or LLM-based QA. So this is based on large language models like ChatGPT and others. Um, the advantage here, these guys are really, they have a huge knowledge. The models is training with billions and trillions of parameters. So they are going to be able to give you answer even if the text don't have it. They also is going to be able to synthesize, summarize, and even reasoning in the text, so they can generate a specific answer, right? Like similar what humans do. The drawbacks here is that some companies they have concerns about data privacy and compliance, so for them it's harder to use online platforms. And the other problem is that there is an extra cost associated because these companies they charge you by tokens, and you have like this constant uh, subscription to pay. It can be a problem for some companies. Okay, so going to the code, I'm going to use this text over here from NASA website. This is talking about the new race to the moon. And this is a hot topic right now. So they're creating this human landing system. There is a transportation of astronauts to the moon using their Artemis program. So the program is managed by this agency, whereas the Artemis mission has this goal or this long-term mission, right, to preserve, to 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 establish a presence of the humans around the moon. So they're talking about they're working with some partners to do that. So this is SpaceX model. So SpaceX has a contract with them, but they kind of think SpaceX is not performing well, and there's other countries as well in this race. And because of that, they also they give opportunities for other companies like Blue Orange. And pretty much this is what the text is about. So I copied it and I put it on this text file. And now I can start to do some code. So the first thing we have to do is to load our raw text, right? So we'll open this file, space.txt, and then we'll say content equals f dot read. So with that, I can read the content. This is space. So I can read the content. And now the idea is, so I have the raw content of the text. I have to split it in sentences. And then once I have it is the sentences split, I need to find a way to rank each sentence and compare the scores of the sentence with the score of the question, see which one is more similar, right? So the first step is to break down the text in sentences. So for that, I'm going to use NLTK. So they have this tokenizer is called word tokenizer, and the one that are really interested is the sentence tokenizer. And let's get the docs, create a variable docs, and then use the function sentence tokenize, pass in the content. And let's do the same for count the words, just to let us know a little bit how many possible tokens we can have. So word tokenizer, content, then we can print this out. Go, then you say sentences and words. So let's see. So it has 17 sentences, 468 words in this document. So we already have the sentences. Just to give you an idea, so this is like how it is. So I have sentence one, sentence two. So we split in sentences. But computer do not understand text like that. So I have to provide to the computer a way that he can compare the questions with the sentences. And but it also needs a number representation, right? So to do that, I can use scikit-learn. They have feature extraction, they have text fixed extraction, and they have this TF-IDF vectorizer. So the TF-IDF vectorizer pretty much convert text in vectors for the computer to understand, but they have a specific logic behind it. So the TF mean term frequency, so they try to see the words that appear more in a sentence usually gets higher score. The reason for that is because if the word appear multiple times is because the central idea of that sentence, right? That's why it gets higher score. In IDF, that means in, inverse document frequency. Try to balance things because if the words start to show up in all the sentences, it means that word is very common. Most likely is going to be an article, a pronoun that's not really give us the meaning of the sentences, right? So IDF tried to balance that and decrease the score in this case. And the same happens for very rare words. Let's say there's a word that just appears once in one document. So this word usually is going to get higher score because it's very rare. So probably it's a huge amount of meaning that word. All right, so let's use it. So instantiate it. I will create a variable doc scores, and then we just do vectorizer fit transform document. So this we're going to have our scores. So this is sparse matrix, and then you have the index of the sentence, so the first sentence, the index of the word in the vocabulary, and this is the score of that word in that sentence. The same for the second one, all the way to the last sentence, the last word. And this is the score for the last word in the whole document. So once we have that, right, so by the way, we need the same from the question. So let's create a question here. So the question is going to be, what is HLS, right? The question also needs to be vector, right? Because this is still regular text. So I have to do the same. Also, like get question score got like equals vectorizer transform, and then I pass the question. Yeah, so now I have, all the sentence ranked. So what I have to do now is see which one is more similar with my question. And for that, I can still use scikit-learn. Then I have metrics, and then I have pairwise. And then I have a function called cosine similarity that is able to do exactly this, compare the question with the answer. And let's get the scores, and let's say cosine similarity, and we'll pass the content in the score. This should be the score, right? And then this is going to give me all the score for all sentences. So based on my question, this is the score for the first sentence, second sentence, third sentence, and go on to the last one. And just by looking, I can see the first one has the high score, so probably this algorithm is correct. So to do that, let's get the best index. What I have to do is np.argmax scores. In this case, I have to import numpy as numpy as well. So this gives me the best index. And the only thing I have to do now is um, to decode back the best index from the sentences, and then I have the text that correspond to this index, right? So this is pretty much in the coding. So let's do this. Let's print the question as well, question answer, and let's see if it's correct or not. That's great. So it returns correctly. So what is HLS? And then HLS is the transportation of astronauts to the moon, right? That's perfect. Um, but this is very simple because the question was very simple is the first one. So how about if I make something harder? For example, Artemis, yeah, this is a good one. Artemis mission are focused on expanding our knowledge and establish a presence around the moon, right? So let's see. Let's see how it works. Let's change our question to what is the mission of Project Artemis? So then I change the question a little bit. Let's print it. You see that returns something really different. It returns SpaceX will perform a demonstration of the mission because he looks at the mission here, he looks at Artemis here, and there's 2 times mission in this question, in this text, in this sentence. And probably this one gets a higher score because of that. And the problem is actually that this method don't know what its mission means in this case. This mission here is different from the goal. Like this is a mission. It's different from the mission of the project. So this is the vision of the project, right? So that's the problem of this model. But that's okay. So let's move on to the more modern extractive approach. So for that, we have to use deep learning, as I mentioned. Let's go and use transformers from Hugging Face. And then we can import the Roberta from question answer model. This is a specialized model to question answering. And we are going to need also the Roberta tokenize. That's the tokenize from this model. So this tokenize do the same thing. You convert text to numbers in the way the computer can understand it and somehow do some correlation to understand the meaning, right? And to start this model, let's create a model name variable and we call it deep set Roberta base quad2. This is the name of the model. And then I'm going to create the tokenizer and create a model as well. And then I will set the model in the evaluation mode. And this is going to be used by inference, not for training, right? So this kind of speed up a little bit the process. So just instantiate the model is done. And then now I start to do the transformations, right? So the first one, I'm going to encode my text using the tokenizer. And the tokenizer needs the content question, and it's going to return PyTorch TensorFlows. But also, if my text is too big, that's probably the case, I want to truncate it. In the real world, usually you're going to have multiple documents. In my case, I'm just going to do a single document. So I'm going to truncate only the second. By the way, I have to put the question first in the content as a second. So I want to truncate, but only the second, only the content. I don't want to truncate the content, the question itself, right? That's all I need. So this is I'm going to have a lot of um, IDs from the IDs from the text, right? And what I have to do now is model. I have to use the model. Get the output of the model, passing my encoded text. And what this model is going to return is going to return for me the starting index in the index on my text that I can use as a reference, as an answer for my question, right? So to extract that index, let's say start logits, and I will say that the start logits come from my output, start outputs, start logics, and my end logics come also from my output. So just to see how it is, let's start. So it gives us this score for each word, that which one is the potential beginning of my answer. So the one that has the highest score is usually the index of the first word in this process. Okay. So okay, but this is not exactly, this is a score, it's not exactly an index, right? So to get the index, I can create a start index, and then I will I'm going to use torch to get the argmax from this list of scores. The same thing for the end index. And now that I have, let's say, print start index and the end index. So I know that from the index 102 to 118 is where it is my answer. So this is an interval, right? So what I have to do now is get all the index, all the tokens that I have in this interval. So let's call answer IDs. And then I'm going to use encoded my tokens, right? So tokens is in this list of IDs. I'll get the first, and I will say that I want from the start index to the end index plus one. So that's my list of IDs. So let's print this. So it should go start index, end index plus one. Okay, this is wrong. Or max and logistics, logits. So now too many uses for tensor of the dimension. Input IDs, the start and end index. Okay, so probably I'm not able to print the index this way. So let's try to get the answer directly. So I'm going to use my tokenizer to decode this list of index. And then probably I'm going to have an answer now. So let's see what I'm doing wrong here. I have the max score from the logistic and so until here we know that's correct, right? And then I'm going to get my IDs from encoded with IDs. Okay, so this is the symbol that's wrong. Okay, I wanted this interval, and now I decode it. So let's print the question again, and print the answer. That's it. Good. So we have the result now. So what is the mission of Project Artemis? So it's give us exactly the answer, expanding and establishing long-term human presence around the moon. So you see how good it is. So we understand the mission, we understand the project, on the taxes as program. So pretty much this gives us a way more accurate answer, right? And yeah, so that's pretty much end this little demonstration. I hope you like it. Thank you for watching.